This video is for lesson 15-6, solving a system of linear equations using matrices. In the previous section, we learned how to solve a matrix equation by multiplying both sides of the equation by an inverse matrix. This gives us a technique to solve a linear system, which we solved this year back in chapter 3. To do this, we want to rewrite the system using matrices. Here's an example problem. Let's solve this system by using the same technique in the previous lesson. So we first have to make this into a matrix. We're going to start by creating a coefficients matrix using the coefficients of the x and y's from these two linear equations. So 2, -3, and then on the next row, 1 and 4. These numbers are the coefficients of the x and y terms from both equations. Now we're going to multiply by another matrix. In the previous lesson, we called this matrix A, but this time we're going to put the variables x and y here. This is equal to a third matrix called the constants matrix, and it's going to contain the constant numbers from the two linear equations. It'll contain the 1 and the 6. So that's what goes on the right side of the equals. This matrix equation is equivalent to this original system of linear equations, because if you really multiplied the left side together, you would have 2 times x plus -3 times y. Notice that's what this first thing here says. And when you multiply using the second row by the column, it is 1 times x plus 4 times y. And look, that's what's right here. So this is how you can change a system with two equations into a matrix equation. Now if we want to get the letter x and y alone, which would be what solving the equation is, we need to remove this matrix out front. And we can do that using the same technique from the previous lesson. Let's first find the inverse of this. And I'll do that over here in the left margin. That involves going 1 over the determinant. So 2 times 4 is 8 minus 1 times -3. 8 minus -3 is an 11. And then we'll make a matrix with 4 entries. Switch the 4 and the 2. Change the sign on this number and this number. Then multiply that 1/11th to all 4 of those terms. That matrix that you get is the inverse of this matrix here. And so when you multiply that to the left side of this, what happens is it will cancel away and you'll have the letter x and y alone on the left side of the equals. We would also need to multiply that matrix right here on the left side of this matrix 1, 6. So when we do that, we're going to have xy equals, and now our inverse that we figured out, it's 4/11ths, 3/11ths, -1/11th, and 2/11ths. I'm writing that on the left side of the matrix that had 1 and 6 in it. Then when we actually perform that multiplication, we will have solved for the x and the y. So let's do that next. 4/11ths times 1 is 4/11ths plus 3/11ths times 6, which is 18/11ths. 4/11ths plus 18/11ths is 22/11ths, which reduces to 2. Now let's do this bottom number. -1/11th times 1 is -1/11th, plus 2/11ths times 6 is 12/11ths, so we have -1/11th plus 12/11ths, and that makes 11/11ths, which reduces to 1. Do you notice that you can now tell the answer for x and the answer for y? So in chapter 3, when we were solving systems, we would find the ordered pair x, y that solved the system. And that's what we need to do here. We get the answer 2, 1 in parentheses. There's our ordered pair. Let's summarize the method that we just used in that example. Step 1, we wrote the system of equations as a matrix equation using this pattern. we wrote a matrix that had the coefficients of the x and the y. Then we wrote a matrix that had the variables x and y. On the right side of the equals, we wrote a matrix that had the constant numbers from the original system. In step 2, we figured out what the inverse of the coefficients matrix is, so that in step 3, we could multiply that on both sides of the matrix equation. And in the final step, remember to record the answer as an ordered pair. You know how sometimes when you're trying to find an inverse to a 2x2 matrix, that the determinant is 0 and so it has no inverse? If that ever happens, that means that the system is dependent or inconsistent. Those were those special cases where there were no solutions or there were infinitely many solutions. Let's try another example using this technique of solving a system of equations using matrix techniques. So the first step, rewrite the system using matrices. 5, -2, 2, -1. Times, and now a matrix containing the letters x and y. Equals, and now a matrix containing the constants 1 and 0. To get x and y alone, we need to remove this coefficients matrix. And to do that, we're going to multiply by its inverse. So on the left side, let's find that inverse. 1 over its determinant. 5 times -1 is -5 minus -4. And that makes -1. Then, switch the -1 with the 5, change the sign of this, change the sign of this. 1 over -1 is -1, and when you times it to these four numbers, that will change their signs. We're going to take that inverse and multiply it on the left side of this matrix and on the left side of this matrix. What will happen is, on the left side, the x and y will now be alone. On the right side, let's actually write down that we're multiplying two matrices. So our inverse matrix is 1, -2, 2, -5. Remember, we had figured that out over here on the left. When you take that number and you times it to those four numbers inside there, these are the numbers you get. We want to times that by the 1, 0 matrix. So here's what we're going to get for an answer when we do the multiplication. First of all, it'll be a 2 by 1. And to get this top number, 1 times 1 is 1, -2 times 0 is 0, and so it's 1. Now let's get the bottom number. 2 times 1 is 2, -5 times 0 is 0, and so it's 2. We have the answer 1, 2. Let's check this new method of using matrices to solve systems against one of our older methods to solve a system. Let's redo example 2 and use linear combination, which was one of the two ways we learned earlier this year. Remember, we had linear combination and we had substitution method. Let's solve it with the linear combination. So I'm going to copy down the system from example 2. It was 5x minus 2y equals 1, and 2x minus y is equal to 0. And we'll solve that with linear combination. Let's keep the top equation the same as it is, but transform the second equation by multiplying by -2. Now we'll have -4x plus 2y equals 0. And we will combine these linear equations by adding in the columns. 5x and -4x makes 1x. The y terms cancel, and 1 plus 0 is 1. We have x equals 1. Now that we know the answer for x, we can substitute it into either of the original equations. For example, right there. So we have 2 times 1 minus y is equal to 0. So 2 take away y equals 0. Therefore, y equals 2. And we have the answer 1, 2. So linear combination method worked pretty quickly for this system. Certainly, if the numbers were more complicated, then this would take a little more work. But you know what? The matrix method was fairly fast as well. If this seems harder, It might be because we're just now learning about matrices. If you do more practice with matrices, you might find that you like the matrix methods better than the algebra methods.